I'm moving on to the notes on the next example. As I'm looking at 8 and 25, is there a number I can take out of both 8 and 25? The GCF is 1, but does taking out 1 really do anything for us or affect the factors? No, it does not. So what do we do if we can't factor something? What do we say about it? I'm actually going to go back to the factor trees for a moment. So 8 breaks down into 2 and 4. 4 breaks down into 2 and 2. 25 breaks down into 5 and 5. So what about something like 13 that I can't break down into smaller factors? What do we call those special numbers? Prime numbers, wonderful. So this is a prime number. This quadratic that can't be factored is a prime expression. So prime. It can't be broken down into Do you want to just sit right here?
No.
Or you can sit in Kale's spot today if that helps.
I'm not seeing any impact though, so it's
Okay, I'll try to zoom in a bit more for that.
Thank you.
Yep. So prime number can't be broken down into something times something. And something times something, that's the less fancy way, I guess, of saying factors. Factor trees represent the things we multiply to get an item. Factoring breaks us down into something times something else or other things we multiply by to get a given item. So folks, that is what GCF factoring looks like. Now, we won't always be able to factor out a GCF, but it's always the place where we want to start when we are factoring because it can make our numbers smaller, and sometimes, like on these problems, it is the only way that we are able to break it up into factors. So folks, we're going to now move into factoring monic expressions or factoring when our A value is 1. So let's go ahead and take a look at this first expression. Now, looking at A, can I take a number out of everybody? This has a coefficient of 1, so using that strategy of yesterday of looking at the smallest number and trying to take its factors out of everybody, if our GCF is 1, that's not really going to help us with factoring this. What about variable-wise? Can I take an x out of everybody? Ooh, yeah, so that 35 doesn't have an x that we can take out, so there is no GCF. But we don't say that it is prime because we have another method of factoring these monic expressions. I want you up here where we wrote our standard form, I want you to put a multiplication sign by C and a plus sign by B. And this is how the factoring process works. We want to find two numbers that give us, first, a product of C, and second, a sum of B. And this was sort of that X game thing that we were doing yesterday, where we were trying to find a product of the top number and a sum of the bottom number. It's just this time we are using it in the context of factoring. So let's go ahead and look at A. And we want to find a product of our C value. So I'm going to put a little multiplication sign there. And a sum of my B value. So I want two numbers that give me a product of 35 and a sum of 12. Now, sometimes the factors will jump right out at you, like they did for some of you guys yesterday when we were trying to solve those little number puzzles. Other times, you may just have to start listing out factors. This is not required work, but you might want to if you get stuck. So 1 and 35 would give us a product of 35. Negative 1 and negative 35 would as well. So to get positive products, sometimes both of those items would need to be negative. What's another pair we could have? 5 and 7. This is going to be our pair that works because it gives us both a product of 35 and a sum of 12. So we have solved the puzzle, we have figured out the two numbers, but now what do we do with them? How do I say that when I multiply two things together, I am going to get this standard form quadratic? So going back to those problems, that one problem that we did back here, if we look back at this standard form expression, a product of -8 and a sum of -2 would give me the factor numbers of -4 and 2. So these are the numbers that work for getting the product and the sum number. And then I use x and x as the first part of the binomial because when we FOIL, that's what's going to give us the x squared part of the quadratic. So for the monic factoring, it's always going to be x and some number and x and another number. So we have to solve the puzzle and figure out what those numbers are, but the first terms of those binomials will always be x and x. So let's go ahead and start this one with x and x in parentheses. My two numbers that I determined are 5 and 7, so I'm going to say plus 5 in this one and plus 7 in the other one. Does the order of those factors matter? Or I guess what I'm asking is x plus 7 and x plus 5 the same pair of factors? Is 7 times 5 the same as 5 times 7? Yes. Is x plus 7 times x plus 5 the same as x plus 5 times x plus 7? Yes. Multiplication is commutative. So when you are checking yourselves on the answer keys for this, it doesn't matter what order you have those parenthetical terms, so long as you have the right numbers and the right signs. So checking the signs is going to be key on this. So folks, those are our factors of that quadratic, which means -7 would be an x-intercept and -5 would be an x-intercept. Now, as we start getting practice with factoring, we could check ourselves by refoiling this. First times first, x squared. Outside terms, x times 5, 5x. Inside terms, 7 times x is 7x. Last terms, that's that FOIL acronym, that gives us a product of 35. And folks, if I combine these like terms, 5x and 7x together, do we get the same quadratic that we started with? Yep. So factoring doesn't change the value of the expression. It just changes the way that it looks so that we can easily find the x-intercepts. X-intercepts are -5 and -7. If I was looking at the standard form, I would have to say, well, first we got to find the axis of symmetry, so -b over 2a. Then we got to plug that into the equation, find the y value of the vertex, center of the vertex in the table, and keep going until we catch those x-intercepts. That is a lot more work. Factoring is more efficient. So if you're feeling kind of betrayed going, why didn't we learn factoring first? It's because to understand what the x-intercepts are and why we care, we need to understand what the graph looks like. So taking a look at B. Do we have a GCF or a number or a variable we can take out of everybody? No. And spoiler alert, with these monics where we only have an A value of 1, you're never going to be able to take a number out of everybody. And if you have an A, B, and C term, the C term will never have an X with it, so you're never going to be able to factor out a variable or a number from these monic expressions as well. So we should still get in the habit of checking for a GCF, although on these problems, we won't be able to have one. So let's go ahead and take a look at our expression. We want to find two numbers that give us a product of 3 and a sum of -4. So my product is positive, my sum is negative. What does that tell me about the two numbers? They're both negative. So I'm going to start with factors of 3. So two numbers that give me a product of 3, 1 and 3, or negative 1 and negative 3. Which pair are we going to pick? This one. Because negative 1 times negative 3 is positive 3, and negative 1 plus negative 3 is negative 4. So our factors will be x with one of the numbers and x with the other number. Order doesn't matter. You could just as easily have x minus 3 times x minus 1. Any questions so far? So let's take a look at our next one. No GCF number, no GCF variable. So we see that our A value is 1. So we're going to solve this using normal factoring, where I'm looking for a product of negative 36 and a sum of 9. Now, yesterday I said with numbers like 60, 36, 144, numbers that have lots of different pairs of factors, you might find it helpful to use the following strategy. We start with the number 1 and pair that with the correct factor. So 1 and negative 36, or negative 1 and positive 36. Does either pair give me a sum of 9? No, it does not. So now I divide 36 by 2, my next integer. 2 would be paired with negative 18 or negative 2 with positive 18. Do either of those give me a sum of 9? That's a no too. So then we try dividing by 3. 3 gets paired with negative 12 or negative 3 with positive 12. Does either of those pairs work? Which pair will give me a sum of positive 9? We need the 12 to be positive and the 3 to be negative. Now, if those ones didn't work, then we try dividing by 4, 4 and 9. Then we try dividing by 5, which doesn't work. Then we divide by 6, and as soon as I get the 6 and 6, we start going up the factors, and the next one that we get is 12. That ensures that you have checked all possible pairs. So we don't write that it's prime because we got lazy and we're like, yeah, those numbers aren't jumping out of me. I'll just write that it's prime. We do want to make sure that we have tried every possible combination to determine whether there is a pair. So the factored form, x minus 3 and x plus 12. And again, if you wanted to, you could check it by FOILing. D is the one that usually messes students up. They sometimes throw this one on the ACT just because when you first glance at it, it's tempting to give the wrong pair. So folks, I'm going to put up an incorrect pair of factors, and I want you to tell me why it doesn't work. X minus 2 and x minus 3. Why isn't that pair correct?
Because it'll just make this 6 positive.
Perfect. So this gives us a product of positive 6, even though it does give us a sum of negative 5. This is why it's important that we always check the product number first, and then we check the sum number, because the two numbers have to satisfy both. So if you're like, well, if those don't work, what will work? A product of negative 6 could be 1 and negative 6, or negative 1 and positive 6. Which pair will give me that sum of negative 5 that we want? The 1 and the negative 6. So x plus 1 for the first factor, and x minus 6 for the second one. How do we feel about these? Good, bad, horrible, wonderful. Here's what I would like us to do. Let's see, where do we have space? We're gonna use all that space. Let's see. You know what, folks? We've got some room on the front of our note packet. I want you to turn back to the first page, and I'm gonna give you a few of these quadratics to try factoring. So number 1, x squared minus 8x plus 16. 2, x squared plus 7x minus 8. 3, x squared minus 5x plus 4. And 4, x squared minus 11x minus 60. So writing these on the first page of your note packet, I want you to take some time and practice factoring these. 60 has lots of pairs of factors, so you may need to list out all of those integer pairs that work to verify that you have tried all of them. Good luck. Product of the C value, sum of the B value. And I'll give you a hint, none of these are prime. And once you get all 4, I want you to compare with someone sitting close by to you. Raise your hand if you're done with the first 2. Raise your hand if you're done with the first 3. Raise your hand if you're stuck on that last one. All right, let's go ahead and start talking about these. So on this first one, product of 16, sum of negative 8. What are the 2 numbers? Being careful with our signs. Minus 4 and minus 4. Now, with these factors, there is a slight trick. When I get 2 factors that are the same, we can write this in what is called condensed form as x minus 4 squared. Another thing that's special about this particular factorization is that 16 is what we call a perfect square number. It has roots of 4 and 4. 4 times 4 gives me 16, so it is a perfect square, and those are the factors that give me the 16. Identifying those perfect square numbers we're going to work on a little bit later, but it kind of gives you a place to start. If I have 144 as the C value, maybe I start with 12 and 12. If I start off with 100, maybe I start with 10 and 10. So identifying perfect square numbers can help you with your guessing. On the next one, product of negative 8, sum of 7, positive 8 and negative 1 satisfy both of those criteria. On this one, our product's positive, the sum is negative, so x minus 4 and x minus 1. Now on 4, what I did, because I looked at that and went, nope, nothing's jumping out at me, I started going up through the integer factors, starting with 1 in the number, and then I just started dividing 60 by all the next integers. I can divide it by 2, 2 and 30. I can divide it by 3, 3 and 20. Then I tried dividing it by 4, and I saw that 4 and 15 do work if the 15 is negative. So folks, if you aren't as great with factorizations, or if you're having trouble getting those numbers to jump out at you, you can always make a list of the factors off to the side, just making sure you're considering the signs for the product and the sum. Folks, what questions do we have so far? Let's go ahead and flip back to page 4 then. And we are going to look at these special factor patterns. Now on problem A, under special factor patterns, do I have a GCF? Nope. What part of standard form are we missing? The B value. So if it makes you feel better, this quadratic in standard form would look like this. So that would mean I'm looking for a product of -4 and a sum of 0. What two numbers satisfy that? -2 and +2. So 2 times -2 gives me -4, and 2 plus a -2 gives me that sum of 0. But this one actually is what we call the special case difference of squares. Actually, all 3, A, B, and C, are all difference of squares. And what's nice about difference of squares is it is a shortcut for normal factoring, and our A value is 1, but it's also a shortcut for the factoring we'll be doing tomorrow. So how we identify difference of squares: first, difference means subtraction, so a minus sign. So do we have a difference? We do. Then we want to ask, are we taking the difference of 2 perfect squares? Is x squared a perfect square? It is, because x times x gives me x squared. 4 is also a perfect square because 2 times 2 gives me 4. So once we identify it as difference of squares, we can take the perfect square factors of the first item, the perfect square factors of the second item, and then the signs in between are a plus and a minus. If you're like, I don't really care for that much, this is the first time you're seeing it. It is a shortcut when we start moving to non-monic expressions or when our A value is not 1. So if you want to always throw in that 0x and use that as your sum number, you absolutely can. But let's do a little bit of practice to see how this works. So first, I see that I only have 2 terms. Is x squared a perfect square? Yup. Is 100 a perfect square? Also yes. And since it is subtraction, this is difference of squares. So I'm going to make my parentheses and do my perfect square factors of x squared, x, and x. My perfect square factors of 100 would be 10 and 10. 1 gets a plus and 1 gets a minus. And does that satisfy our expression? 10 times a -10 is a -100, and 10 plus a -10 does give me 0 for that inner term. So folks, that is my factorization. If your buy-in is still kind of low, take a look at problem C. Ew! First, this is our first problem where our A value is something other than 1. We're going to see how the X method works tomorrow, but in the meantime, we, without knowing what we know tomorrow, would not be able to factor this. But we see that 36 and x squared are perfect squares. We see that 49 is also a perfect square. So what are my perfect square factors of 36x squared? Perfect square factors of 36 would be 6 and 6. Perfect square factors of x squared would be x and x. Perfect square factors of 49, 7 and 7. One gets a plus and one gets a minus. And we have just factored that. And when in doubt, don't forget that you can always refoil to check. 6x times 6x, 36x squared. 6x times negative 7, negative 42x. 7 times 6x is positive 42x. And then 7 times negative 7 is negative 49. The outside and inside products cancel, and we are left with that original expression, 36x squared minus 49. So what about this? We're going to sidebar up here for this one. What about x squared plus 25? Can I factor that?
Yes.
Let's try a pair. What do you think? If we do positive 5 and positive 5, will that work? No, because it does give me positive 25, but it would give me a middle number of 10. So 2 positive 5s are out. What about x plus 5 and x minus 5? Does that work? Nope, because that will give us a product of negative 25 instead of positive 25. So that's out. So how about negative 5 and negative 5? Does that work? It gives me a product of positive 25, but what sum number does it give me? Negative 10. So folks, what can we say about this expression? It's prime. And I just want you to put a warning by this that goes, there is no sum of squares. There is no sum of squares. So if you see two perfect squares joined by a plus sign, you can automatically say that it is prime, as long as there's no GCF that you can take out, which there wouldn't be for this one. There is no sum of squares. So let's skedaddle on down to problem D. See if you can find the combo for that one. What are the factors for D down at the bottom? Anybody find them? X plus 3 and x plus 3. Because we're looking for a product of 9 and a sum of 6. So the factors happen to be the same. So we can either write it as x plus 3 times x plus 3, or we can write it in that condensed form that says x plus 3 times itself, or x plus 3 squared. I like the condensed form because, it's less work. Now, the other thing I want to put on your radar with this problem is what's special about the number 9? It's a perfect square. So that kind of prompts me, anytime I see value as a perfect square, to try the perfect square combos first, either positive 3 and positive 3 or negative 3 and negative 3. Now, it doesn't mean that will always be the pair of factors, but it gives us a place to start. For example, if I had x squared plus 10x plus 9. Does 3 and 3 work for this one? No, 9 is still a perfect square. What would be the pair of numbers that work? Product of 9, sum of 10, would be x plus 1 and x plus 9. So you could draw a little cloud around that. So knowing that your C value is a perfect square won't always take you directly to the factors, but it does give you kind of a nice place to start. So for example, as I look at E, it jumps out at me that 81 is a perfect square. Do 9 and 9 work? They're close. What do we need in front of those 9s? Negatives. So x minus 9 and x minus 9 will work. Because this is negative, we have to have the minus signs, or we can write it in that condensed form, x minus 9. If you're like, all right, it wouldn't have taken me very long to find those factors, oh, Mrs. Cairo. 64 has quite a few different factor pairs to try. But if we have it on our radar that 64 is a perfect square, and we try 8 and 8, we see that that does give me the sum number of 16 that we wanted. So this would be x plus 8 squared, or x plus 8 times x plus 8. Now here's the dealio with the homework so far. I actually don't have anything in the purple packet with factoring quite yet, because in the purple packet, this is where you will get to put all the combinations of factoring methods together. GCF, difference of squares, and what we'll be doing tomorrow, which is X method factoring. So I don't want you to do anything on here until we've seen the X method. That way we can actually practice putting it all together. So what we're going to do next is actually do some practice on delta math. So you'll see that I added it to the back board there. This is actually assigned. It will put you ahead of the game if you do decide to do a retake for this unit. So go ahead and take out your computers. And I want you to hop on Delta Math and find the 4.2 assignment. And we're going to be doing the first 2 skills.